All right. So I repeat the introduction. So, dear colleagues and friends, thank you very much for being here. It's our pleasure to welcome you today, Mr. Wonho Choe, to
Right.
our department, to our series of seminars in the PhD program of Aerospace Engineering. Wonho Choe is a professor in the Department of Nuclear and Quantum Engineering of the Korea Advanced Institute of Science and Technology, KAIST. And he's going to be talking a little bit about the institute
Yes.
for the first 15 minutes. He's also working as a joint professor in the Department of Physics and Department of Aerospace Engineering at KAIST. So as we are here, Aerospace Engineering Department, that's quite nice. He was a pioneer in electric propulsion research in Korea, with a particular focus on Hall thrusters. And over the past 2 decades, his group has been developing more than 25 laboratory models for Hall thrusters, and some of them became actually the basis of prototypes or industrial thrusters that are now flying in space. From 2021, his group, together with the Korean Aerospace Research Institute, were leading a mid-power Hall thruster of 5 kilowatts, more or less.
Right.
And his research interests include also physics and applications of low temperature weakly ionized plasmas and the development of advanced imaging plasma diagnostics, such as plasma tomography. He has received many awards. I don't know if we need to go through all of them, but the KAIST Technology Revolution Excellence Award, Academic Award from the Korean Vacuum Society, Prime Minister Achievement Award, Ministry of Education, Science and Technology Achievement Award, and he has recently published a paper in Nature, which was also recognized as one of the top achievements in the scientific research in Korea in 2022. Then he holds some, he's vice chair of the Association of Asia Pacific Physics Society, and other chairs that I think we can skip if you agree,
Okay.
and we can directly jump into your talk. Thank you very much for being here.
Okay.
And floor is yours, please. I think you have.
Okay. Thank you very much. Wow, this is a very detailed introduction. It's my great honor to be here. Particularly, I'd like to thank the Professor Ahido, although this is my first time to visit Madrid and also Spain. I've visited Portugal, Lisbon, 2 or 3 times, attending European Physical Society, but not in Spain. About 10 to 15 years ago, there was a chance to attend a conference in Spain, but because of my project evaluation, I had to get my funding, which was more important compared to attending a scientific conference here in Spain. Anyway, I would like to spend a few minutes on introducing our institute, named the Korea Advanced Institute of Science and Technology. Although it has a name institute, it is actually a research-oriented university, such as in MIT. So you can visit this website for getting more details. So if you fly from Spain to Korea, then you're going to get to this Incheon Airport, which is a huge international airport. And from Incheon Airport to Seoul, which is the capital of South Korea, is about 1 hour, by bus. And we are 160 kilometers in the southern, direction from Seoul. So which takes about 1 hour by KTX train. KTX train means Korea Train Express, which runs something like a 300 kilometers per hour. And also you can get to Daejeon, this city, in less than 2 hours by express bus. So we are located in Daejeon city. As in Madrid, located in pretty much in the center of Spain, Daejeon is also located pretty much in the center of South Korea. Here, Japan. Here, this is the KAIST campus, main campus. We have 4 or 5 different campuses, 2 campuses in Seoul and 2 campuses in Daejeon. And this is the main campus, having like 1.5 million square meters. And we are located in so-called the Daedok Science Complex. So we are surrounded by many national institutes. KFE is a Korean Institute of Fusion Energy. KARI is an Aerospace Research Institute. KRIB is a biotechnology institute. And other national labs are also located in here. I would say KAIST is the best science and technology university in Korea. There are 7,000 grad students and 3,600 undergraduate students are actually attending this school. And about half of the graduates proceed to industry, and about 1/3 go to university to become university faculty members, and government and the research institute about 1/4. And I'm not sure what it means, but according to the QS ranking, we are something like 39 or 40 in the entire world. And this KAIST was established in 1973. So a couple of years ago, we actually celebrated a lot of this 50th anniversary. And what else? I like to point out that about 25% of Samsung, you know the Samsung, big company, Samsung's R&D workforce are actually KAIST graduates, which is pretty a big number. And nearly 20% of all Korean universities' engineering faculty are also KAIST graduates. So these are two important figures, like this person is the CEO of Samsung Electronics, and this person is the CPO, is Chief Production Officer of LG. All these guys are KAIST graduates. Our university emphasizes very strongly about the international cooperation, including many of the universities, institutes worldwide. And I found that UC3M is not in the list, so maybe in the future we have this. We have to go for that. And the World US University ranking is growing. You know, it's going up annually, which is what we are proud of. And we have a pretty strong program in material science, mechanical and aerospace, chem engineering, civil, electrical engineering, chemistry. The physics department is something like in between 40 to 50. So I spent like 20 years in physics department, and about 5 years ago, I moved to a nuclear and quantum engineering because I wanted to learn more about engineering. In the last 3 years or so, as everybody suffered, we also suffered the COVID-19. So about 3 years ago, the Korean government invested something like 30 million euros only to KAIST to develop something good for fighting against the COVID. So this is not a research money, only development. So at that time, the president of KAIST strongly emphasized that nobody writes a paper, nobody writes a journal paper out of this product in close collaboration with the industry. So among them is something like this amount, and the technology development commercialization was the main target. And many of the about 500 KAIST members joined, not only staffs, research staffs, professors, but also many of their grad students. And one of the items is a low temperature plasma medical sterilizers. So we were given something like how much? More than $2 million of research development funding to develop these plasma sterilizers. This is the short introduction of KAIST, and I'd like to spend a few minutes on the plasma group. So before going into that, if you have any comments, questions, ask me. Okay. So in our department, there are 4 professors, including myself and Professor Youngcheol Kim, Chung Gi-sung. These 2 guys have been working on mostly a nuclear fusion plasma, talking about plasma. And Professor Sung joined about 3 years ago, and before joining KAIST, he spent 2 years in LEM Research, US, which produces low-temperature plasma equipment for semiconductors. So he has also an industry experience. And Professor Sang-Woo Park was my former grad student. He got his PhD degree from our group, and he specialized in low-temperature plasma. Not only experiment, but also modeling. We have about 40 graduate students in our plasma group, and about half are working on basic plasma research and applications, and another half are working on nuclear fusion plasma. For fusion side, I have led this Impurity and Etch Plasma Research Center, which is a multi-university nuclear fusion research center for 13 years. And then now we have an integrated model-based center for developed technology, which is a continuation of the research center. This is also a multi-university center having 3 universities and 1 national research institute. And we have been focused on R&D for demo-grade developed technologies. So in the developed plasma, plasma temperature is very low compared to the core side of the plasma, relatively speaking, low-temperature plasma. We have 2 linear devices for hand-on experience, for providing hand-on experience for grad students. Again, developer and boundary plasma physics and the diagnostic development, advanced imaging, machine learning-based data analysis techniques, and so on. For basic plasma research and plasma application side, we have been working on basically plasma physics and the chemistry, plasma liquid interaction, plasma functionalized water, and the RF plasmas for semiconductor display applications, supported mainly by industry like Samsung or LG. Plasma diagnostic development, and so on, and plasma application and feasibility studies. I want to mention briefly that PlasmaMap is the acronym of Plasma Smart Application, which is a startup company established in 2015 out of my plasma group. And they actually worked very hard. We started like 5 people, and now they have 160 people working on this. And then this company recently became successful in IPO, initial public opening in KOSDAQ, Korean stock market. So you can actually buy stocks internationally. Specialized in medical sterilizers based on plasma technology. Pictures show some examples, and this one was published in Nature a couple of years ago. And I'm going to cover this maybe in the later, so I'm going to just briefly skip this one. And we have developed many advanced state-of-art plasma diagnostics, spectroscopic diagnostics, including laser Thomson, Raman, LIF, this 2-dimensional LIF system, and TD, laser absorption spectroscopy, soft X-ray diagnostic system, which is an imaging system, 2-dimensional, and the FTIR, optical absorption emission spectroscopy, interferometer, and so on and so forth. And many of the electrical and magnetic probe diagnostics, of course, including Langmuir probes, arrays, and the retarding potential analyzer, E cross B, Vin filter, Faraday probe, beta probes, and so on and so forth. We were lucky to publish our result in prestigious journals, and our work was selected by the Korean government last year as the best achievement among 2022 top 100 national R&D outstanding achievements. So people are recognizing our work. So this is again the plasma, the product. StelLink, this is the very compact medical sterilizers for dentists and also orthodontics. And they recently got a contract with the US animal hospitals. So we are expecting to export a lot to the US. And this piece, we got the US FDA certificate, which is the first non-US company acquired this certificate. And this one is for surface treatment and also sterilization of the a small titanium bolt for implanting, your teeth, your tooth. So you can actually, when this is turned on, you can actually see the plasma doing, plasma treatment, surface treatment. So people are paying a lot of attention, and we are actually showing this in many medical equipment exhibitions, worldwide exhibitions. So this is it. This is a brief, I hope I was able to finish the introduction of KAIST and plasma group.
Maybe we can keep our questions for the end, and we can do the
Okay. Okay.
Yeah.
Okay.
Thank you very much.
Okay. So now a brief introduction to the KAIST electric propulsion group. Spend 10 minutes or so. These are the PhD degree graduates from the EP group. So Hola Kim and Keun Tae-do, these two guys are working in Korea Aerospace Research Institute. And he got an offer from the Busan National University, and KAIST is actually working very hard to have him as a faculty member. So he is going to expect the interview with the KAIST president in the next couple of months. So we're going to see what's going to happen. Yu-bong Lim is the CEO of the PlasmaApp, the company. Jong-sub Lee is working right now in Samsung Electronics. Mi Seo, the lady doctor, she's working at the Agency of Defense Development. And Dr. Lee is in Korean Institute of Material Science. Dong-ho Lee is a postdoctoral researcher at Georgia Tech, working with Dan Lev. So as you can see, the job spectrum is pretty wide, and we are closely working with them. Right now, I have 5 PhD degree grad students, PhD course grad students. Young Ho is working on xenon, krypton propellant and the mixture of it. Jae-hong Park is working on modeling. Jae-jun Lee is working on cathode neutralizer development. Not only heaterless, but also cathode with a heater. Dong-ha Park is working on CubeSat, 2U CubeSat, together with Sang-soo Kim. So over the years, we actually started our EP research in 2000 to 2003. And I was deeply thinking of what kind of direction I have to take. And my conclusion was the way toward the kilowatt class is not the way to go. Because at that time, 20 years ago, a few 100-watt, like a 200, 300-watt is niche. Not many people were working on that lower power hot thruster at that time, 20 years ago. Not only that, but also Korea has a heritage of producing 150 kilogram, 250 kilogram small satellites for science and technology purposes. So for those small satellites, 200 watt, 300 watt, even up to 500 watt Hall thruster is the way to go. So that's why I chose developing 300 watt Hall thruster. So over the years, our target was to develop like a 10 millinewton or 15 millinewton and so on and so forth. So we have developed many of the Hall thrusters in that power range. Smaller versions like KAIST Hall thruster 30 millimeter in diameter. 40 millimeter became the flight model for SDSat-3 satellite. And the 5070, these are larger power like 600 watt, 700 watt class. And then we went further down to like a 20 millimeter in diameter, 15 millimeter in diameter, and so on, focusing on targeting like a 2 millimeter, 3 millimeter class Hall thrusters. Here, CHT means cylindrical Hall thruster, M means magnetic shielded. Okay. So a variety of more than something like 20, 25 different engineering model or laboratory model Hall thrusters were developed. Currently, we have developed the 100 millimeter in diameter, like kilowatt class, similar to the SPT-100 Hall thruster has been developed. And 130 is the 2 kilowatt class. So we developed this one 3-4 years ago. And now we are developing 5 kilowatt, 200 millinewton Hall thruster. And although this is a TBD, but diameter is going to be 140 or 150 millimeter. So these pictures show part of the Hall thrusters that we have developed over the years, like the smaller versions up to the biggie ones, the larger one. So these are the annular Hall thrusters, cylindrical Hall thrusters. And our Hall thruster became the base model for commercialized, these two commercialized Hall thrusters developed by Satric Eye. Satric Eye is the company in the area. It's, if I drive, I can reach in like 15 minutes of driving. So they sold their satellite together with this Hall thruster to Dubai Sat2, and this Deimos satellite is actually a Spanish. So this company bought this satellite and then operated for a few years, and they sold this to a Canadian company. So it's still working, and this Hall thruster is still working. So it's pretty good. My own group developed a flight model for SDSat-3 is Science and Technology Satellite 3. So we have a heritage. We have been aiming at the 50 to 1,000 kilogram class satellites. This one shows the smaller version. Is a typical cell phone, Samsung cell phone. And this is a small size of Hall thruster of about total diameter is about 2 inches or 50 millimeter. Depth in here is a 35 millimeter or so. As you can notice, you know, this was developed basically by grad students. So we didn't put a lot of engineering in it. But if we collaborate closely with the industry, then it's going to look like much nicer version of this. But anyway, it's working. You know, it's working fine. And this will be the base model for the Hall thruster for 2U CubeSat. It's a 50 watt class micro Hall thruster. Recent development, we developed a couple of years ago 700 watt class Hall thruster with 4 electromagnets. And the power consumption is something like up to 1 kilowatt, down to half of a kilowatt. Thrust is 30 to 50 millinewton range, and the typical T over P, or thrust power ratio, is in between 45 to 60 millinewton per kilowatt. And as you can notice in here, colors are different. So xenon, krypton discharges. Last year, we developed the 1 kilowatt class Hall thruster. As you noticed, we developed 2 different versions, one with a 4 electromagnet version, and this is coaxial version. It's working fine, and this one actually puts better performance compared to the 4 electromagnet version. So this one consumes in between 700 to 1500 watts, producing 50 to 80 millinewton. T over P value is in between 55 to 65 millinewton per kilowatt. And the anode efficiency is up to 57%. This one shows my laboratory experimental facility. We have 2 chambers. We started from this smaller version, like a 1.8 meter in length and 1 meter in diameter. Xenon pumping rate is not that great, 4,000 liters per second. And then about 10, 12 years ago, we acquired this larger vacuum chamber. So 3 meter in length and 1.5 in diameter, and the xenon pumping rate is about 24,000 liters per second. So when we operate like 1 kilowatt class or 500 watt class Hall thruster, then the operating pressure is low 10 to the minus 5th torr, which is pretty okay, I believe. This one is the shows the backside of the chamber. As I mentioned before, the xenon pressure, operating pressure, is low 10 to the minus 5th torr during experiment. We have 4 cryopumps, 2 on the top, 2 on the side, with a big gate valves. Diagnostics, as far as diagnostics is concerned, we don't have a lot, but okay, I think. So we have a typical Faraday cup retarding potential analyzer and floating emissive probes and double long-wave probe for measuring potential profile in the far plume region. And we have an E cross B probe for measuring multiply charged ion species fraction. And we have a 3D tomographic reconstruction together with the optical emission spectroscopy. So this is not the picture. This is actually tomographically reconstructed the emission coming from the plasma in the plume region. So this was reported last year's IPC. And the guy who presented this one got the poster prize out of that. We have been also, yeah, I have to mention this one. Laser-induced fluorescence was developed about 4 or 5 years ago. This is a 2-dimensional, so we can actually follow ions in 2-dimensional way, RZ plane. So I'm going to show you that. And we have been also developing this hollow cathode. This is the original pretty large one, and the recent development is very compact, producing like a 1 ampere or 2 ampere current, electron current. We have 2 thrust balances here, 2 of these, and the accuracy or measurement accuracy is something like less than 20 micronewton. So this is pretty okay, pretty good accuracy for measuring 10 millinewton or several tens of millinewton thrust. It's a typical pendulum type balance. This one is the -1 version, flight model -1 version Hall thruster for STSat-3 satellite. The total power we were given is 230 watts. Because if you want to build a Hall thruster system for the rear satellite flight model, the power budget is really, really tough, very tight, and also mass budget. So requirement is very, very strong. I mean, for ground test, you can just plug your Hall thruster to the wall, right? So power is unlimited in some sense. But in the air, I'm sorry, in the orbit, this power budget is really killing. So 230 watt altogether. So we have to share anode, electromagnet, cathode, everything. And you have to communicate with the ground, right? Ground station. So you have to properly distribute all these powers. And the anode power, 200 watt, and the thrust we were producing was 11 millinewton. Anode efficiency was about 36%. ISP was about 13,000 seconds. So this one shows the SDSF3, 170 kilogram, 300 watt, which was launched in 2013, exactly 10 years ago. And this one shows, again, the thrust head module, propulsion control module, and the power processing module, and the genome feeding module. So it's a small integrated system. So this picture was taken just before launch. It's bottom side of the satellite. You see the cathode in here. It's a typical hollow cathode. We purchased it from the heat wave, the notorious heat wave. But it worked fine for us. It is a laboratory model because I actually called the owner of the company asking about availability of flight model, and his answer was almost impossible to meet. So we decided that we are university guys, and our funding was really limited. What can you do? Okay, let's give a risk. So we bought laboratory model, and then we just prayed, working. It worked fine. So this one, commercialized version, again, Dubai Set 2, Demos 2. And for Dubai Set 2, you can notice the cathodes are different, right? For this one, it's a hollow cathode, but one is a redundancy. For Dubai Set 2's satellite, this is an ECR-based cathode. And from JAXA, ISAS JAXA, from Professor Kuninaka. And Professor Kuninaka approached me, and he explained that he wanted a flight heritage of this cathode. So JAXA actually provided this cathode free of charge, which is very, very expensive, It would be something like at least 200,000 or 300,000 euro for development. Flight model, I mean. So it worked fine, and this one also worked fine. You know what? This is also heat wave cathode, laboratory model. So this company, Satrec I, bought about 10 of these cathodes, and then they selected it, And these hollow cathodes are prone to contamination if this is exposed to moisture, oxygen. So you have to be very careful. You have to keep it inside nitrogen, very carefully. So this DM2 Demos satellite, the Hall thruster was operating and used for collision avoidance. So by operating the Hall thruster for 3 days, 4 days, they actually changed the orbit by 1.5 kilometers. So it was working. We are now working on developing CubeSat. It's called the K here. K means KAIST. So KAIST Hall effect rocket orbiter. My grad student actually named it. Very bright. So the main purpose is a validation of the Hall effect thruster performance by estimating the change of the orbit's semi-major axis by the thrust. So it's, the orbit is going to be 600 kilometer sun-sync orbit. Mission period is 1 year. Expected launch date is May 2025. It's still in the very early phase of development. This is 2U, but recently the CARI is the managing institute supporting this one. And this will be launched by a Korean launcher in 2025. So they informed us that they have more room. So we're going to develop 3U instead of 2U, which is actually better for us, better to us. So the mass is going to be about 3 kilograms. The payload is the Hall thruster. Total power is going to be like 120 watt, anode power of about 70 watt. Thrust is a 3 millinewton, specific impulse about 700 seconds. So as you go down in size, then the performance efficiency actually drops. So that's why the numbers are a little bit smaller. So this is the conceptual, design. So Hall thruster, 4 antennas like horns, and the genome feeding unit and the power processing unit, and these are going to be the lithium-ion batteries. Numerical simulation activities, we are still in the very beginning phase of modeling, so that's why I'm here to learn from you. So we have a CAPC-1D hybrid electron fluid and the ion, particle code. Actual hybrid peak code works with the GUI application. So this is used for calculating plasma properties and performances. We have a whole bunch of experimental data, so we can actually very easily compare modeling result and the experimental result. And we have been developing this CAPC-2D, which is an actual azimuthal hybrid peak code. And the development is ongoing. It already produces some result, which was reported IPC last year. And this is mainly for investigating anomalous transport. Very fancy looking calculation result. And using the data obtained through conventional numerical methods, we add deep learning techniques in here. So deep learning based CAPC-1D code for predicting anomalous transport rate. And we have been working very hard to on this one, Hall thruster performance prediction, which the conventional or the usual scaling the Hall thruster development is based on empirical, result. And hopefully our code can provide some sort of a complementary function to this. We have been working very hard to align to the Korean roadmap, development roadmap. So mostly until now we are in here 2022, 2023, and this shows a full line of small or large satellites developed in Korea and which are all in orbit. So mostly based on chemical propulsion. And 2013, as I mentioned before, we have a Science and Technology Satellite 3 having our Hall thruster, 200-watt Hall thruster. And in the future, like a GEO satellite GK3, LEO satellite, and another GEO satellite, the CARI is very seriously, significantly thinking of having electric propulsion. So eventually going to a full EP. So GK6, where is GK6? 2030 or so. So if everything goes very well, so we're gonna utilize the EP technology for the Korean satellites. So we are way behind compared to NASA, ESA, JAXA, but we are working hard. So we have a 1 kilowatt Hall thruster technology, shooting for 5 kilowatt, and from 2021 up to 2026, so in 5.5 years, we have been working on developing 200 millinewton Hall thruster electric propulsion system development, not just the Hall thruster, but also the full system, which is a qualification model. So if you just take the flight model, the flight grade components, then it becomes flight model. So qualification model, flight model, technology level is pretty much the same. So we are going to develop this qualification model of 5 kilowatt. The funding is altogether something like $50 million US dollars by the industry, research, National Research Lab, and KAIST consortium. So we provide the engineering model. And Kari is putting a lot of engineering on that together with the industry. And the integration, ground test, lifetime test, and so on and so forth will be done by this AP satellite company. Specific impulse, about 1,500 seconds, thrust at 200 millinewton. The efficiency, total efficiency, not just the anode efficiency, but total efficiency of something like 50%. And space verification will be done by Korean satellite launcher, KSLV, about 2030. And this is just the target, goal. Taking 5 of these satellites, putting 20 kilowatt. So for ground test, we are actually constructing the test facility, and the total length is about 10 meters, and the diameter is about 4 meters, and the smaller version is going to be also fabricated and installed on that. Pumping rate is going to be 100,000 liters per second, and the KAIST, we don't have a land, so Kari Aerospace Research Institute, they have a space for hosting this one. Also, Kari is leading low power ion thruster development, shooting for like a 10 millinewton small version. And we are very new in ion thrust development, so it's going to take some years. Okay, that was the brief introduction of EP Group in Korea. Okay, I'm going to very quickly go through. So electric propulsion, why is it important? We all know because you are experts on EP technology, so I'm going to just very quickly go through. Now, this is the trend. After 2015, 2017, the number of rocket launches has been going up quite steeply, and the satellites, launched satellites go exponentially increasing, lifetime becomes reduced, mass becomes reduced. So why is that? Thanks to the reuse of a SpaceX rocket. So this is the trend. Lifetime, something like 2 years or 3 years, it becomes disposable. Okay, so this is the trend, smaller side. So new space, so-called, we are transiting from older space to new space, and the new space requires low power EP. So the target, development target, is something like 300 watt or less, satellite mass of 100 to 30 kilogram. So very compact EP system for disposable uses. I mean, if you think of a Starlink or OneWeb, they are shooting like 10,000 satellites having either 1 or 4 Hall thrusters, 300 watt or 400 watt. Lifetime is again 2 or 3 years. You have to, replace a lot of satellites. So this is not a joke. Small, low size, low power EP market is not a joke. And as you can see, as you reduce the power consumption, efficiency drops down. So we need a plasma science-based R&D, not just a trial and error type of engineering approach, no longer valid. So we have been working on both annular type and cylindrical type Hall thrusters. As you can see, the plume structures are very different. Why cylindrical Hall thrusters? Why? Because if you reduce the size of the Hall thruster, then plasma volume to surface ratio also reduces. You lose a lot of energy particles, momentum, to the surface. So how can you increase the plasma volume to surface ratio? Get rid of the inner pole. So by doing that, the magnetic field topology becomes very different. Now, not only radial component of the magnetic field, but also axial component of the magnetic field becomes really important, which brings about quite interesting physics. So we have experimentally noticed a larger fraction of multiply charged ions, xenon, not only xenon plus, but also 2 plus, 3 plus, even 4 plus, highly charged xenon ions. And the fast ions are having xenon kinetic energy larger than charge times anode voltage, fast ions. And also high frequency oscillations. One explanation is, again, the ion transit time type of instability and the extensive ion extraction outside the thruster exit. As I mentioned before, the magnetic field in annular type is pretty much radial, but in the case of cylindrical Hall thruster, these PR and BZ are quite comparable, which makes a lot of differences. So as you plot the x-axis as a power, anode power, thrust, anode efficiency, ISP, these were all, each point is a experimental point. We used various different kinds of Hall thrusters, about the same size, but with a different magnetic field geometry. So as far as the thrust is concerned, annular performs better at the fixed power. Efficiency also higher, but ISP, cylindrical Hall thruster, performs better. So you can actually choose either AST, CST. What do you want to choose? If you are very tight in power, if you are very tight in propellant, you can just choose. Okay, it's not. It's a issue of an option. Multiply charged xenon ions, as you can see, in the case of annular type, mostly xenon plus and a little bit of xenon 2 plus, but in the case of CHD, a larger fraction of 2 plus and 3 plus, even a small peak in CHD 4 plus. This is the E cross B probe spectrum and RPA spectrum. As you can see, xenon plus actually makes a large population of fast ions. Okay, here anode voltage was 225 volt. X-axis is the ion energy per charge, and thus a larger fraction of ions exist in CHD. And we also observed something like a 360 kilohertz frequency, and together with the 14 kilohertz breathing mode. This one shows the different electric field structure along ion trajectory based on the two-dimensional LIF system. So if we just plot just this much of the plume, this much of the plume, then electric field is mostly dominant in the exit region. However, as you can see in here in this diagram, the CHT, in the case of CHT, this electric field stretches pretty much out in the plume region. So again, in ion energy profile, this is the thruster exit. In the case of annular type, ions become accelerated with kinetic energy, average kinetic energy, and ions become accelerated mostly in less than 10 millimeter or so. However, in the case of CHT, the ionization region is mostly in here, but the acceleration region is further stretched out up to like a 60 millimeter, 70 millimeter. Magnetic field tailored CHTs. So these are conventional cylindrical type Hall thruster. Magnetic field lines look like this way. And then we distorted magnetic field a little bit to cope with, and then we reshape the anode like here. So you can see more flatter or more parallel magnetic field lines along with the wall. So what are the performances? MCHT shows, in general, higher performance in thrust, anode efficiency, and also specific impulse compared to the conventional CHTs. So I can go through, that was a very brief summary of that, and then I can go through one by one very quickly, or I can stop here and then get questions. We have 20 minutes. Continue, okay. Very well. Okay. So comparison between annular and the CHTs, again, plume angle, CHT very broad, AHT narrow, IDF nearly Gaussian, in the case of CHT, nearly Gaussian with a shoulder. Ion species, a larger fraction of multiply charged ions in CHT, fraction is something like 30%. Thrust to power ratio, AHT performs a little bit better. So in here, we changed the geometry of the CHT a little bit. So this is the depth of the CHT, 90 millimeter, 22, 25 millimeter. And in general, deeper the better. Okay. In radial, we fixed this depth, and then we changed the radius of the Hall thruster. So there's a pros and cons. Okay, with a larger one, with a larger diameter, smaller diameter. With a smaller diameter, specific impulse is a little bit better. Propellant utilization is a little bit better, but you lose thrust just a little bit, and the plume angle becomes larger. So you have to optimize. Okay. And we had a little bit of this depth. Our intention was to utilize this region for pre-ionization. Okay, so if in this small, very narrow region, electrons are produced, and these electrons can become the seed electrons for bulk ionization in this region, but no good. Okay, once you have this, then no good. So just a flat geometry is performed better. And in CHT, according to the conventional definition of propellant utilization, so as you see, the definition of propellant utilization is that you provide a xenon gas, how much you get the ion current out of that. So it's ionization efficiency, right? And according to the conventional definition, CHT propellant utilization is all more than 100%. Doesn't make sense, right? So we were really puzzled. So, and then came up with developing the equal-speed probe, and then we had this one. So in AHT, mostly xenon plus ions, a little bit of 2 plus and 3 plus, but in the case of CHT, a large fraction of 2 plus, 3 plus. Okay. Why? Because of the geometry. It's a geometry of the magnetic field. This is the radial center. The radial center magnetic field is going toward the axial direction, right? Parallel to the thruster axis. So slow ions reside in here, having a large residence time, going through, experiencing stepwise ionization. So stepwise ionization potentials for xenon plus going to the next stage is only 20 electron volt, to become 3 plus 30, 32, and then to become 40%, 46 electron volt. So these electron, energies, this much of energies can be provided by electrons inside the bulk, inside the cavity. So we wanted to check whether our measurement is correct or not. So we modified the calculating the formulas for calculating thrust, and here instead of mi.vi, we included the multiply charged ions in it, and calculated thrust ratio is about 1.47. Thrust ratio is CHD divided by AHD, and measured ratio is about 1.4. So it's consistent, not 100% exact, but close enough. I already mentioned this one. So we have a large fraction of fast ions. And when we get this one, experimentally, we always observe 360 kilohertz. However, not all the time. When the mass flow rate was 4 SCCM, we don't see any, very clean. As we increase the mass flow rate to 6 SCCM and the 10 SCCM, we see this. And as we increase the m dot, then this peak size increases further. In the case of AHT, very calm, no. And the measured IEDF, ion energy distribution function, you see this kind of big shoulder, mostly due to the xenon plus ions, because xenon plus ions are the slowest one. It's very slow compared to 2 plus or 3 plus, right? Inside the cavity, inside the near radial center region. So longer residence time, more chance of stepwise ionization, producing, multiply charged ions. So we set up, our postulate was, okay, the potential profile is moving in and out. Electric field is moving in and out. Okay, based on this kind of hypothesis, we set up the equation of motion and then calculated, solved this quantitatively. So x-axis here is the oscillation frequency, y-axis is the ion energy per charge. And for xenon plus, 2 plus, 3 plus, we solved the equation of motion. As you can see here, 14 kilohertz breathing mode locates, and then 360 kilohertz is right here. In the case of xenon 2 plus, the peak ion energy matches with the 360 kilohertz. In the case of 2 plus, peak is shifted here. 3 plus, peak is further shifted toward the higher frequency side. So our observation is pretty much consistent with the this calculation. So electric field is oscillating in and out, pushing the back of xenon 2 plus ions. That's how xenon 2 plus ions get further energy than the anode voltage. This is again the two-dimensional profile of the ion trajectory and the mean ion energy. So we were following ions along trajectory 1, trajectory 2, trajectory 3 and 4. And this one shows the emissive probe measurement potential. Why up to here? Because if you put the emissive probe further inside, then plasma becomes perturbed. So that's why the probe had to, place further, away from the thruster. Okay, so these are equi-ion energy profiles. This one I already showed ion energy profile, in the case of CHT, the acceleration region is further stretched out. This one is interesting. In the case of CHT, the angle between the magnetic field line, magnetic field line and these equi-energy lines are not actually perpendicular. So in the case of annular type, we all know that the electric field and the magnetic fields are perpendicular with each other, right? In the case of CHT, not anymore. So there's an angle existing in here, in between magnetic field line and the electric field. So you have to provide, your modeling guys, numerical simulation should provide why. I think I already showed this one. So in here, conventional CHT, tailored magnetic field, or the tailored magnetic field tailored, or the magnetic shielded, the plume structure near the surface in here look different and more parallel. Performs better. So in the case of MCHT, higher fraction of multiply charged ions is closely related to, performance is closely related to these multiply charged ions, we believe. So this is the summary. Time is tight, so let me just stop here. Thank you very much.